Imagine two of the most precise clocks ever built, calibrated independently, constructed by the greatest minds on Earth, running without a single flaw for over a decade. But they disagree. Not by a lot. Not in a way you would notice walking past them, but in a way that makes every physicist in the room go completely silent. Because in science, a small disagreement between two perfect instruments is not a rounding error. It is a message. Right now, the universe is trying to tell us something. It is expanding, stretching in every direction, carrying galaxies away from each other like raisins in a rising loaf of bread. We have known this for nearly a century. But when we try to measure how fast that expansion is happening, our two most powerful methods give us different answers. And no matter how many times we recheck the math, recalibrate the instruments, or rerun the simulations, the disagreement will not go away. This is the Hubble Tension, one of the deepest unsolved mysteries in modern science, and scattered somewhere in the ancient light bending around massive galaxies, there may be a clock the universe has been running for billions of years, one we are only just learning to read. Welcome back. Today, we are going into one of the most elegant ideas in modern cosmology, a technique called Time-Delay Cosmography, a method that uses the warped fabric of spacetime as a cosmic stopwatch and potentially the key to finally understanding what dark energy actually is. Let's get into it. To understand why this matters, we need to go back a century. In 1929, Edwin Hubble discovered that galaxies are moving away from us, not because they are physically traveling through space, but because space itself is expanding. To describe how fast, physicists use a number called the Hubble constant, written as h0. The larger it is, the faster the universe is stretching. Measuring it precisely has been one of the great obsessions of modern astronomy, and today we have two dominant methods. The first uses the cosmic microwave background, the CMB, the ancient afterglow of the Big Bang itself. By studying the faint temperature patterns in that 14-billion-year-old light, physicists can mathematically reconstruct how fast the universe should be expanding today. The answer they get is roughly 67 kilometers per second per megaparsec. The second method works in the opposite direction. Instead of the early universe, we look at the nearby universe, using Type 1a supernovae as what astronomers call standard candles. These stellar explosions have a consistent, known brightness. By measuring how bright they appear in the sky, we can calculate their distance, map the expansion directly, and arrive at a Hubble constant of roughly 73 kilometers per second per megaparsec. Both methods are sound. Both are peer-reviewed and replicated worldwide. And yet, they disagree by nearly 9%, a discrepancy sitting at 5 sigma. In the language of physics, that is not statistical noise. That is a result robust enough that particle physicists would declare a discovery. Something is wrong. Or more excitingly, something is missing. The scientific community has spent a decade trying to make this problem disappear. Maybe the CMB analysis has a buried error. Teams have combed through it. It is not there. Maybe the supernova distance ladder has a flaw somewhere in its chain of measurements. Groups around the world have audited every link. The ladder holds. So the conversation shifted. Perhaps this is not an error at all. Perhaps this is physics. Perhaps dark energy, that mysterious force driving the acceleration of the universe, is not a fixed constant, as Einstein proposed, but something dynamic, something that has evolved over billions of years in ways our models have not accounted for. What we need is a third method, one built on completely different physical assumptions, free from the potential blind spots of the other two. One that uses the universe itself as the instrument. In 1936, Einstein described a phenomenon called a gravitational lens. When an extremely massive object, a galaxy, sits between us and a distant light source, it bends the light around it. The distant object appears not once, but multiple times, split into several images arranged around the lensing galaxy. But here is what Einstein did not fully explore. An astronomer named Sjoerd Refstal spelled it out in 1964. When light from a single source splits into multiple images, each image has traveled a different path through bent spacetime. Different path lengths, different depths in the gravitational well, and that means the images do not arrive at the same time. This is the time delay, and its precise value is set by the geometry of the universe, which is directly controlled by the Hubble constant. Think of it this way. Imagine firing two signal flares from the same location, and they travel around opposite sides of a hill before reaching you. The hill changes their routes. One path is longer. One passes closer to the summit, where the terrain slows it differently. You measure the gap between when each flare arrives, and if you know the shape of the hill, you can calculate exactly how far away the launch point was. The lensing galaxy is the hill. The quasar, an ancient, violently bright object powered by a supermassive black hole, is the signal flare. And the time delay between its multiple lensed images is the measurement that unlocks the distance, and, from that, the Hubble constant. Astronomers monitor these lensed quasars for years, watching their brightness flicker as matter spirals into the black hole. Those same fluctuations appear in each image, offset by days or weeks. By measuring that offset precisely and modeling the lensing galaxy's mass, teams extract a Hubble constant that shares no systematic errors with either the CMB or the supernova ladder. The leading collaboration doing this work, H0LICOW, analyzed 6 lensed quasar systems and arrived at a Hubble constant near 73, sitting firmly on the side of the local measurements, deepening the tension rather than dissolving it. The method is not without its challenges. Lensing galaxies are complex, messy structures. Mass sheet degeneracy, the ability to redistribute a galaxy's mass in your model and produce the same images but a different Hubble constant, is a genuine mathematical headache, one that requires independent observations of how stars move inside the lensing galaxy to break. But the future of this field is arriving fast. The Vera Rubin Observatory is expected to discover thousands of new lensed systems over the coming decade. The James Webb Space Telescope is already imaging these systems with a resolution that was unimaginable 5 years ago. And within 10 years, the statistical power of time-delay cosmography could reach a precision that forces a definitive answer. If the tension holds, if every independent method keeps pointing to the same disagreement, then our standard model of cosmology is genuinely incomplete. Dark energy is something stranger than we thought. The early universe hid a secret we have not yet uncovered. And if the tension finally breaks, if the methods converge, we will have learned something equally profound. That precision works, that the universe is consistent, and that we are capable of reading it. We built civilizations under these stars. We told stories to explain their patterns. And now, for the first time in all of human history, we have instruments sensitive enough to measure the delay in a flickering light that left its source before our sun existed, and use it to weigh the fate of everything. Stay curious. Keep questioning. The universe does not owe us simple answers. It just leaves clues.